Hi students. Okay, so this is our second part of chapter 6. It could have been possible to do all of chapter 6 in one part given the pace, but it is probably a good idea to take a break between the chapters here, between the parts here, because finishing the first part of our unit normal table and using the unit normal table to find set scores and proportions, the only sure way for a student or any person for that matter when you're doing this for the first time to practice this skill is to work with practice problems. So it is very important that when you work with the unit normal table and find proportions using set scores or with set scores, or trying to find set scores with proportions, that you have ways to practice them. So here are some resources that you can use first. First, you can use the questions from the slide that you've worked with, obviously, if you've been watching the video so far. Other ways include finding questions in our textbook, which is available here. Or using questions from our module. So here we're looking at chapter 6, probability. So again, we have other resources too that can help you from crash course videos. And these web tutorials, you want to use Microsoft Edge for Windows or Safari for Apple if you are using Mac OS. It doesn't work on Chrome, unfortunately, because it's disabled Flash. But once you allow the Flash in a compatible browser, in Windows it would be Microsoft Edge, then you can actually try these questions out. And it actually shows you the steps of doing it. So for example, is Z values greater than Z equals negative 0.125? Well, again, it's greater than. We're looking for a proportion. In this case, is greater than, so it's going to be to the right of the distribution. So let's check that if that's true. Again, that's greater than. Let's see. Aha! I read the question wrong. It says here, is the value of Z at negative 0.125 is on the right or the left side, not whether the proportion I'm looking for is on the left or the right side. And so, for example, if you were to answer incorrectly, which I did just now, it would tell you why all the positive set scores are greater than the mean are on the right side and all the negative values are less than the mean. Less than the mean, that means it's on the left side. So you take this next step. Okay, the Z at negative 0.125 or 1.25 is on the left side, so values greater than. Would that be the body or the tail? So it's on the left side, and values that are greater than is going to be to the right, which I was thinking of, but didn't answer the correct question or the right question. So the proportion then for values greater than Z equals negative 1.25, that would be, let's see, the body. Because we're looking at values of Z that is going to be closer to the mean and then above the mean. Correct. So if I answered incorrectly, the tail, it would, it didn't let me do that once I made this correct response. So next question, step 3 of 3. Well, I know it's going to be the body portion of the Z. And so if I go back to my unit normal table and go 1.25, okay, I need to look at the body, and that is 0.8944. So let's see if I entered that. 0.8944. Well, let's see. Can I scroll down here? Submit. Correct, I've entered that, and that's my answer. That's the proportion I'm looking for. 8944. So, yes, you can. You can practice this interactive web tutorial or web tutor. Again, use Microsoft Edge for Windows and Safari for Apple. And so that's one great resource that you can use right away. Another resource would be the textbook itself. Again, you can download this. Once you got the textbook, you can go into the textbook and locate chapter 4. That's chapter 11, that's really far. Chapter 6, chapter 3. Oh, no, we're not looking for chapter 4, we're looking for chapter 6. So, here we go. Chapter 7, getting closer now. And notice, for each chapter, there are a whole bunch of problems and practice questions you can work with. Okay? And you can check the back whether there are answers to odd number questions or even number questions or to all the questions. But again, the key is if you're able to do the questions and do your own self-check and be sure that you've checked and you got it yourself, then you are prepared for a test. If you're relying for answers, well, you're kind of halfway there because you're still relying on an answer. You haven't gotten really the answer yourself. So the steps are also there available for you to try. So if you're working with a textbook, yes, you can work through the problems, but also you can follow the book and do the steps yourself. Write down the steps as you go on their own sample problems, so then you can go through the textbook as if, you're being taught by the textbook. Again, these are resources that are available to you at any time, and you can study at your own pace. So the rest of this video recording then goes through the last part of this chapter, starting with 6.3. So remember, the probability for normally distributed scores, well, they can only work with normally distributed scores because we need a consistent way to find the probabilities. And the only way to do that is with normally distributed scores from normal distributions. And think, you can also see that the Z scores are standardized scores, and the unit normal table or the Z table is working with standard normal distributions. So then, as the rest of this slide says, when we do probabilities, we want to make sure that the distribution is normally distributed before we start using the unit normal table. For the purposes of this course and the questions you're going to get related to this chapter, yeah, you can assume for now that the population is normally distributed. In other courses where you will be taught and asked to test whether that assumption is true, whether the population is normally distributed, there are techniques for doing this, and you'll have to write out that assumption. That would be covered in other courses that are more advanced than this one. This is the basic level that assumes that the population is normally distributed, so then you can apply the unit normal table for these probabilities. When we do have normally distributed scores, then we can change the X scores into Z scores, if we're working with X's, and then find the proportions using the corresponding Z scores in our unit normal table. So here's an example. We have a distribution of IQ scores, which in a way is also standardized, but we first want to transform the score. In this case is the X of 120, that's our value, and we know the standard deviation for this population is 15, and the population mean is 100. So we calculate the Z first. So again, you can calculate the Z for this. 120 minus 100 over 15. Well, that's 20 over 15, which is, well, 1 1/3, which is 1.33. So that's our Z score right there, right? So with that, we want to find the proportion. In this case, the question is asking in terms of the shaded area, well, how much of the population distribution has a IQ of 120 and below. So we know the z-score, so we want to ask, well, is this going to be, what area are we looking for? In our basic scenario here, we ask, is it body or tail? The proportion is larger, and so it's the body. So we look for column B. And so if we look for this in our unit normal table, which is right here, we find 1.33, and when we look for the body, and that is 0.9082. So the proportion here is 90.82%. And that is the probability of a z-score being less than or equal to 1.33, which is 90.82%. Again, if the question was asking the tail, then you would have something like this. Somebody scoring 1.33 standard deviations or above, and you could either go 1 minus 90.82 or look at the tail value, which is the same thing, and that would give us 9.18%. And notice these two proportions add up to 100%. So here's an example where we change the x value into a z-score, and we know the z-score, then we figure out which proportion we're looking for, and then locate that using the unit normal table and finding its corresponding proportion. Here is another distribution for practice. This one is slightly harder because we need to do more steps. So the question asks here, well, what is the probability of, you can write this in two ways, of an x value being 55 or above, or 65 and below. So an x value of between 55 and 65, including those values. Well, that is also the same as writing it. Okay, we found the z-score, so it's negative 0.3, and then it's plus 0.7. Again, if you weren't given these values for practice, you would need to calculate it. So, for example, the lower z here, well, let's call this z1 and call this lower and upper, I suppose. Here you go, okay, well, it's x minus mu over sigma, so it's 55 minus 58 divided by 10. Well, that's a negative 3 over 10, which is negative 0.3. And very quickly you'll see that, oh, well, this is the z upper. Well, same thing. We find the z-score. So that's 65 minus 58, 10. So that's 7 plus 7. So it's plus 0.7. So we have our z-scores. Again, if you're familiar with your z-scores, that's fairly easy. So here there's a couple ways to do this. The simplest way, probably, is to find two proportions using the D column. So column D, so we can call this area A, and this area B. So then we go, oh, okay, well, it's area A plus area B. So we need to find the first area first. And so it's between 0 and 0.7. So we find 0.7, which is right here, and we can actually find the two values at once. Again, it's between the mean and the z-score. So 0.7 has a proportion of 0.2580. 0.2580 plus 0.3. Oh, okay. So again, it's negative 3, but again, since this normal distribution is symmetrical and we're looking for column D, we find positive 0.3, and that proportion in column D gives us 0.1179. 0.1179. So again, remember, we're adding those two areas together to answer the question. What is the probability of somebody scoring between 55 and 65? So we add these together. That would give us 1, 3, 7. Let me write it properly. 3759, which is 37.59%, or 37.59% of the population scored between 55 and 65. And again, the only way we could do this is first transforming the raw scores, x values, into z scores, and then using the unit normal table for us to find the corresponding probabilities. So the last bit here in this chapter talks about percentile ranks. And percentile ranks, as we recall, well, as you can see in the slide here, is a ranking system where it talks about the percentage of individuals in the distribution that has a score that is the same or less than that rank. So, for example, a 99th percentile would be somewhere here. This is like that 1%. And then 99% of the scores right here would be the same as this particular Z value or lower. And so this score right here, whatever it is, that's the 99th not 99%, but the 99th percentile. So it's not the same as percentage, it's percentile. That's a rank, not a proportion. So again, because percentiles work with percentages that deal with proportions, you can, like the last point in the slide says, percentile questions can be rephrased as probability questions, and probability questions can be rephrased as percentile questions. You just gotta know how to work with percentages and percentiles. Here's an example for something for practice. This is one of the harder questions that you can get. Again, it's the same distribution as before, but we are working with a different area this time. This time it's an area between 65 and 75. So here we're looking for something like this. So there are a couple ways of doing this, and I'm going to show you the simpler way, but I'm going to walk you through both ways, at least logically. You might think, oh, okay. Actually, there's more than two, but there are two ways that are simpler. The first way is, oh, okay, I can find column D between 0 and 1.7, and then this would be our area A, and then subtract that with the smaller area, which is this white bit here, which I'll dot or something as a way to mark it. So then I could say, okay, well, this is area A minus area B. That would give us our shaded area. Another way of doing it is, well, instead of looking at column D, I can also do column B, which is the body. Well, I can go, well, what is column B for, and this is using the D column here. But essentially the operation is the same. There are other ways that do it that is more complicated, that involves looking at the tail, but the two simpler ways is simply subtraction. The bigger area minus the smaller area. So again, if you use the B column, it's the same. And it's still area A minus area B, but instead of area A being between 0 and the Z is now all the way over here. And then area B would be this smaller area. So you can still see that, yeah, it's still the big area minus the smaller area. So we're going to try both ways here and see if we get the same result. This is also a good way if you happen to have extra time to double check, as long as you apply the same logic to see if you really got the right answer. this can apply to things that you've done before, like computational definition, computational formula versus definitional formula. This is another way of double checking your work using logic. So here we go. I'm going to try column D first because that's simpler. So we know the Z scores already, and you can calculate that. So the first one is 1.7. So let's find 1.7. And that gives us, in column D, 0.4554. 4554. Okay, minus. I'm going to save time, I can also look at column B as well. Column B gives us 0.9554. Okay, 0.9554. Okay, cool. So here we go and look for 0.7 again, which is here. 0.7, well, that's in column D, 0.2580. And then in column B, that's 0.7580. Well, if you look at the numbers a little more closely, you can see, oh yeah, the result's going to be the same. Well, it's 554 for area A. The only difference is, well, for the larger area, for column B is 9, starts with a 9, and for column D it starts with a 4. And then it's the same can be said for area B. It ends in 580, but column B starts with a 7, and column D starts with a 2. I mean, yeah, so you're going to get the same result. So, subtracting these then, you're going to get 0.1974. So it would be the same for both of these. And that would translate to 19.74%. And that's the same for both of these methods here. Again, there are more complicated methods. If you happen to look for the tail, which is more work, you could also do something like using the tail portion, that is tail of 65 minus the tail of 75. So then area A would be over here, and then area B would be the smaller portion. Again, it should yield you the same result. So there are multiple ways of doing it, but as long as you are able to locate and shade the area that the question is asking you and find the right combination of parts to either add or subtract, then you'll be able to find the right proportion every time. So then here is a picture that describes the relationship that you get. And starting with the ZX score, you have an X score that you transform into a Z score. And then you would use the Z score to find the proportion using the unit normal table. And you can do this vice versa. That's why the arrows go both ways. And then that will help you answer the question of the proportion of scores that is in some range of X. Again, it could be either larger or equal to X, or less than or equal to X, or between some combination of X values, like some X1 and X2. The harder ones would be where it's not symmetrical, so you have to do some combination of some adding two areas or subtracting one bigger area from a smaller area. So here's one more for practice. And we're going to use percentile here for the wording. So the highest 10%, we'll double check first whether the Z score of 1.28 is 10%, or anything that is 1.28 or greater, whether that is 10%. So we go to our unit normal table, look at 1.28, and then we look at column C for the tail, and yeah, that is close to 10%. It's closest we can get in this table. It is slightly more than 10%, But yeah, that would be close to 10%. So then in this case, a score of 37.1 in this distribution in terms of commuting time would be the 90th percentile, or close to it. It's actually a bit more than 10%, so this would be less than 90%, but for the sake of argument, it's close enough to 90% that we'll say it is for this video. Now, yeah, this would be this score would be the 90th percentile, because 90%, or very close to 90%, but slightly less according to the table, of scores are equal to or below this score. So this whole white area here is the 90% of the distribution of people that, took some transport and had a commuting time of, I don't know, maybe it's minutes, 24.3 minutes with the average. And then, yeah, anything that is 37.1 minutes or less, yeah, that's 90% of the population. And so anything above that would be the other 10%. So again, if you think of news years ago that talk about like the top 1%, well, those who have the wealth of 1%, or the top 1% of the population owning some large proportion of the nation's wealth, that would be the 90th percentile, because 99% of the people have less money than them, or equal to, but probably less. So that's how percentiles work. It is the percentage of the population distribution, or the percentage of the distribution that has the same or the less score than that particular score. So here's another one. This is not percentile, but then this is the middle percentage. Notice here it is the middle because we are not only looking at this part that is above the mean, above the z-score, but also the negative z-score as well. So it's plus 1.65 and minus 1.65. So this would be the middle 90% because we are looking at scores between plus and minus 1.65. Again, you can double check this if you want to see if it's 90%. Again, using column D here because we're looking at the middle percentage. So it's between 0 and 1.65. And so if we look at that, 1.65 is somewhere over here. Yep, it's close to 45%. Again, it's a bit more than 45%. It says 0.4505. So 0.4505 multiplied by 2, that's 0.9010. Again, it's close to 90%, but slightly over. So it would be kind of like this, actually. It's going to be the middle 90.1%. So again, if you're looking at the middle percentage, it's no longer percentile because it would include this too, which would be 5%. So a score of 40.8 would actually be the 95th percentile because it is ranked as the 95th percentile because 95%, not only the middle 90%, but also this 5% on this side, that is equal to or less than this score, which is 40.8. And here for 7.8, this would be the 5th percentile because 5% of the scores is equal to or less than 7.8. In the middle would be the 50th percentile because, well, half the score is equal to or below that point. And so, again, be sure to describe and review the difference between percentile, which is a rank, and the definition of that rank is the percentage of scores that is the same or less than that specific score versus some percentage of the score. Percentile is a rank with all the scores equal to or below it as that rank, whereas a percentage or proportion could be either the middle portion, or it could be the body portion, or the tail portion. So watch out for that. So here then some final learning check questions. Membership in Mensa requires a score of, and this is an IQ test, 130 on the Stanford Binet 5 IQ test. And that test has a distribution of 100 for the mean and 15 for the standard deviation. So what proportion of the population qualifies for Mensa? Again, you can pause and try it yourself. We'll work through this problem with me right now. So, well, it's fairly straightforward. We first find out the Z. Okay, 130 minus 100 over 15. Because the Z formula is x minus mu over sigma. The numbers, standard deviations are scores away from the mean, or the distance between the mean and the score, or the score from the mean in standard deviations. Well, here's 30 over 15, which is 2. And this is plus 2. Okay, so what proportion of the population qualifies for Mensa? Well, again, qualifies here means you got to work out, understand the word problem. Qualifies means, well, 130 or above. And 130 here would be the minimum score. So you want the probability of a Z score being greater than or equal to 2. Well, in that case, well, if we draw out the proportion we want, well, we got the middle here, 0, and this is 2. And so we want this area, when that would be the tail, and so we want column C. So we go to column C, look for 2, and we found it, and the tail is 0.0228. So 0.0228. Multiply that by 100, and that gives us 2.28%. So 2.28% of the population would qualify for Mensa. And you can actually also convert this into percentile, and that would be, well, 1 minus this. You can either look at that through in column B in the body, so that would tell us, oh, okay, 97.72% of the population is equal to or below that score, so that would be at the 97th or close to 98th percentile. So if you answered 0.0228, you're right. True, false here. Okay, so these would be 6.3. Let's change this real quick. Okay, so is it possible to find an X score that corresponds to a percentile rank in the normal distribution? So the statement says, yes, it is possible. So is that true or false? And 2, if you know a Z score, you can find the probability of obtaining a Z score in the distribution of any shape. Again, concept questions. Take a moment to think about the relationship between an X score, a Z score, and the proportion or probability in the unit normal table. So for the first one, if you answered true, you're right. You can find a Z score for a percentile rank and then transform it back to X. So once you know the percentile rank, then you can find it's a proportion. Then you can locate the Z score and then transform it back to X. So for example, the 99th percentile, if you go to the table, look for 99% in the body. In this case, the closest one would be 0.9901. And so the Z score would be 2.33. And then you'll need to know the population mean and standard deviation to transform the score back to an X. And then you have your X right there. And for B, if you know a Z score, you can find the probability of obtaining the Z score in a distribution. Well, this is only true if the distribution is normally distributed. That is, it has one peak, one mode, and it is symmetrical. The question says any shape, and that's false. If it's skewed, you can't use the unit normal table anymore because it is not a standard normal distribution, because a skewed distribution is not a normal distribution. It's skewed. So the table doesn't apply anymore. The distribution shape is different. Looking ahead to inferential statistics then, we would work with probabilities to figure out, for example, how we can compare samples with populations or samples with another sample. Again, probability is also used for random sampling, where everyone gets an equal chance from the population to be selected as a sample. And noticeably different then would be whether a sample distribution or the mean of the sample distribution is far enough away from the population distribution where we can say, yeah, only a very small percentage, it could be 1%, it could be 5%, would have that score, be it positive or above or below the mean. And then you say, yeah, that's really different because only 1% of the people or only 5% of the entire population would have it. So it's not likely. Therefore, it is considered noticeably different. Again, the concept goes like this. You get a population, and then because you can't grab everybody from the population, you get a sample. Okay, from the population, sometimes you know the average and the standard deviation. If you do great, then you can use z-scores. If a treatment is applied, then you would get the treated sample, and then you would compare whether the treated sample, for example, let's say this is the population or the null distribution. We'll talk about that as well, because again, we can't get the population distribution most of the time, so we must approximate it. And so, for example, you have a sample here. If that sample distribution and the mean, falls within that very small percentage on the extreme, then you say, yeah, the treatment seems to have an effect because it's making the sample really different from the population. So let's say if this was the population over here with a mean, and then this one has a sample mean with some x value, which is s. Again, you can review sample variance as well and sample standard deviation. If it's far enough away, then you would say, looking at probability, well, only a really tiny percentage of the people would have a score like this. Therefore, it is noticeably different. And then you can say, yeah, I can decide to reject the idea or the hypothesis that the sample is the same, comes from the same population. And so you might say, oh, okay, well, I think there's some difference there. So that's the concept. Another way to show that concept here is with the probabilities itself. Probability. And so again, if you set a particular region, and we will call this the critical region, where a score is extreme enough in the population distribution or a sampling distribution, which is an approximation of the population distribution, then if a particular sample falls within this extreme over here like that, we'll say, yeah, it's really extreme. It's noticeably different. It's not likely that somebody would get that score. But if it happens to be in here in the middle somewhere, it's within that middle 90% where it's the probability of getting that is much higher, then you say in this particular situation, it's not noticeably different because, it can still come from the sample. Whereas here on the extremes, you say, yeah, these scores are really far away from the sample. It's only a tiny portion of the people would have this, that only 5% would have something larger or smaller than that extreme, 2 standard deviations away. And so you would say, yeah, it's noticeably different. And you would decide to reject the null hypothesis at that point, which means, yeah, we're going to reject the idea that, there's no difference between the sample and the population. But we'll talk more about that in the chapters to come. So again, that's it. We've covered our 5 learning outcomes. We have explained and described the definition of probability. We have explained the assumptions of random sampling, along with the replacement formula of how we can make sure everyone gets an equal chance of being selected to be a part of the sample from the population. We can find probabilities using the unit normal table of z-scores now. We can find scores when we're given a proportion of the distribution, again using the z-table. And then we're able to find percentiles and percentile ranks, as well as transforming x-scores into z-scores to help us find those things, percentiles and percentile ranks, using the z-table. So that's it. Make sure you use your practice questions. Make sure you work them through. Make sure you try as many questions and variations as you can. And if you got any questions, you can go to your resources, work at your own pace, and also ask me via email if you're taking this class with me. Keep going. We'll be applying all the stuff we learned so far into what we're going to call inferential statistics when we start testing hypotheses and approximating population distributions using sampling distributions, where we do a sample distribution an infinite number of times, so then we can get the means from each sample and then use that as a distribution of sample means. But we're going to talk more about that next time. So until then, practice your probabilities using your unit normal table, using algebra and z-scores and percentages and probabilities, and we'll see you in the next one.